In Lecture 4, we learned that nature is made from just 5 elements or essences: atomic matter, light, neutrinos, dark matter, and dark energy. Now, our entire world and experience are concerned solely with the first 2 of these, atomic matter and light. So it's a bit humbling when you discover they're only a minor player, making up just 4% of the current total. So if we want to fully understand nature's great cosmological story, we must obviously get acquainted with the 2 dominant players: dark matter, weighing in at 23%, and dark energy, weighing in at 73%. So I hope by the end of this lecture you'll feel a little bit more comfortable with these characters and the role that they play in constructing the universe. Now, for both dark matter and dark energy, I'm going to be asking 3 questions. What's the evidence that they exist? What role do they play in the evolution of the universe? And what are they, and what are they made of? So let's start with the first of these. How do we know they exist? You can immediately guess why they've eluded detection for so long. Look at their names: dark energy, dark matter. They neither emit nor scatter any light. They are profoundly invisible. Now, this isn't necessarily a disaster for us. I mean, after all, we can't see the air around us, but we know it's there because it influences things. For example, when the wind blows. And it's just the same with dark matter and dark energy. We know they're there because they influence things by their gravity. As we'll see, dark matter is lumpy, so it affects motions between individual galaxies, while dark energy is spread about uniformly, so its gravity only affects cosmic expansion. Now, since we'll be dealing with motion caused by gravity, we need to be familiar with simple circular orbital motion. So let's briefly look at that now. Imagine a large mass pulling on a small mass. If the small mass were initially stationary, it would just fall directly towards the large mass. But if it's initially moving sideways, then the sideways motion and the inward pull combine together, and the upshot is that the small mass travels in an orbit. In this case, it's a circular orbit. Ultimately, that's all that orbits are. They're the combination of sideways motion and an inward pull of gravity. Now then, for those of you who are happy with this kind of thing, let me briefly show you the equations which describe this circular orbit. So we start from Newton's second law of motion. Force equals mass times acceleration. The gravitational force is given by Newton's famous inverse square law, g(m)m/r squared, where g is Newton's gravitational constant and the 2 m's are the 2 masses, and r is their separation. So that equals m times v squared over r, where v squared over r is the acceleration of an object moving at speed v in a circle of radius r. Okay, so we can cancel out the small mass to get gm/r squared equals v squared over r. And we can easily rearrange this to get m alone on the left, and we have m equals v squared r over g, which is an incredibly important equation. Now, don't worry if you didn't follow all of that. The bottom line is that Newton's simple laws of motion and gravity mean that if you know the size and speed of a circular orbit, you can calculate the mass responsible for making that orbit. This is an amazingly useful formula in astronomy, and I'm going to illustrate with a couple of examples. So, first one. The Earth moves around the Sun at about 30 kilometers per second in a roughly circular orbit with a radius of 150 million kilometers. Now, if you plug these numbers into the equation along with big G, you immediately find that the mass of the Sun is 2.0 times 10 to the power 30 kilograms. Bingo! The Sun's mass is measured quite accurately. Now, my second example is much grander. Here's a typical galaxy. Stars in its disk move approximately on circular orbits. Now, in ways we'll get to in a minute, it's possible to measure the orbit speed and size. And let's say they are 200 kilometers per second and 25,000 light years. Well, once again, you simply plug these numbers into our equation, m equals v squared r over g, and we get 1.4 times 10 to the 41 kilograms, or a little over 70 billion times the mass of the Sun. Again, you've just measured the mass of a galaxy. When you think about it, these are quite remarkable results. We'll never go to visit the Sun or a galaxy, but using Newton's laws of gravity and his laws of motion, we can confidently measure both of their masses. Now, the examples I just showed you are for a single orbit. But when the orbital speed is measured for a whole range of distance from the center, we get what astronomers call a rotation curve. It's a graph of orbital speed versus distance from the center. Now you can play the game we just did, but for each distance, and calculate the mass inside each orbit. Here are our two examples again. For the solar system, going out in radius, the planets orbit more and more slowly. So the rotation curve drops. When you plug each velocity and each radius into our formula, you keep getting the same value for the mass, because each planet feels the same mass. It's the Sun's mass, of course. But here's a typical rotation curve for a galaxy. It stays high at all radii. Now, if you calculate the mass within each radius, you find, not surprisingly, that it increases as you go out, because mass is spread throughout the galaxy. But, and this is the important part, if you could measure orbital speeds outside the galaxy, they should drop off, right? Just like the solar system. You're now outside the galaxy, so the orbital speeds should drop. Now, throughout the 1970s, one of the pioneers in this field, Vera Rubin, measured many galaxy rotation curves using Doppler shifts of emission lines coming from clouds orbiting within the galaxy. Now, in essentially every galaxy she measured, the rotation curve remained high right to the very galaxy's edge. Now, this was a little bit unusual, but what's really needed was a way to measure rotation beyond the visible edge. Now, there was a real breakthrough in the early 1980s when radio telescopes began to discover and then measure giant rotating disks of tenuous hydrogen gas that extended well beyond the visible limits of the galaxy. Here's an amazing pair of images. On the left is an optical image of a normal spiral galaxy, and on the right, at the same scale, is a picture of the hydrogen gas taken with a radio telescope. The optical visible galaxy of stars is just the inner part of a much larger disk of hydrogen gas. Now, one of the wonderful properties of hydrogen is that it naturally emits photons with a pure radio color with wavelength 21 centimeters. And so this can be used to measure Doppler shifts. So these rotating hydrogen disks could provide just the rotation curves we were looking for. Now, before I tell you the results of that, I want to briefly show you the kind of instruments that measure this radio emission. So radio waves coming from the sky were first discovered by Karl Jansky in the early 1930s, first from the Sun and then from the Milky Way. And over the years, it's become clear that the radio sky provides a radically different view of the universe. and we'll keep returning to it during these lectures. Now, unlike optical telescopes, radio telescopes are huge. Here are two, in the US and the UK, both with collecting dishes roughly the size of a football field. Now, in the 1950s, a technique was developed which combined the signals from an array of radio telescopes, giving enormously improved sharpness to the image. This one, for example, in New Mexico, has 27 25-meter dishes spread in a Y pattern spanning 36 kilometers, justifying its name, the Very Large Array, or VLA. Okay, back to those rotation curves. Here's a VLA observation of the atomic hydrogen emission in the nearby spiral galaxy M33. Here's the optical starlight image, and here's the hydrogen gas radio image added as blue. And here, the red-blue colours signify the Doppler shifts of the hydrogen gas away and towards us. Using these Doppler velocities, here's the full rotation curve. It continues to rise well beyond the starlight disk, whose predicted rotation curve should fall like this one. These two curves are really very different and show that there is a significant mass outside in the halo, beyond the stars. Now, here's a second example that provided the first clear evidence for massive dark halos back in 1985. The optical galaxy sits within a large hydrogen disk, shown here using white contours, and the rotation curve stays flat way out beyond the stars, whose predicted rotation would fall well below the observed rotation. The only way to match that rotation curve is to add in a new component of mass, and it's labelled here as the halo. Now, I want to stress that the hydrogen gas itself is very lightweight. It's less than 1% of the mass needed here. Instead, we need something several times more massive than all the stars, yielding essentially no light. That is what's referred to as the dark matter halo. Now, with these new observations, we need to look at galaxies with a fresh eye. This is what they're really like. Whenever you see a galaxy, you must think of this whopping dark region around it. It's a bit like an iceberg. The visible galaxy is only about 1/6 of the total, most of which goes unseen. Now, galaxy rotation curves are not the only thing to reveal the presence of dark matter. Let me quickly review the evidence for dark matter in clusters of galaxies, which, if anything, is even more convincing. When you take spectra of the galaxies in clusters like these, you find Doppler velocities of several hundred kilometers per second. Now, although the galaxies aren't on nice circular orbits, it turns out that instead you can use the average galaxy velocity in our simple equation m equals v squared r over g to find the mass of the whole cluster. Now, the mass you calculate turns out typically to be 25 times more than all the stars in all the galaxies. So clearly, there is lots of invisible matter present in the clusters. Now, amazingly, this result was first found way back in 1933 by the famous Swiss-American astronomer Fritz Zwicky, who measured the Doppler velocities of galaxies in the Coma cluster. But for reasons that aren't entirely clear, his correct conclusion that galaxy clusters contained large amounts of invisible matter was never really widely accepted. And we had to wait until the 1970s to rediscover this result. Though in retrospect, Zwicky is now acknowledged, of course, to have been the first person to have discovered dark matter. Now let's look at two completely different approaches to measuring galaxy cluster masses to see if they give the same result. The first makes use of the fact that galaxy clusters have huge atmospheres of extremely sparse but extremely hot gas, which is held down by the cluster's gravity. These hot atmospheres emit X-rays, and so they can be seen using X-ray telescopes, such as NASA's Chandra satellite. You can see that they show up as large, smooth blobs filling the cluster. In some sense, these cluster atmospheres are actually similar to our own atmosphere. Their height has adjusted so that its outward pressure just balances the downward force of gravity. It's a condition called hydrostatic balance. So, using the X-ray images to measure the height and temperature of the gas then yields the downward gravitational force, and it's that that tells you the cluster's total mass. Now, fortunately, the results agree almost perfectly with the masses derived using galaxy velocities, so that's encouraging. Now, it's important to check, of course, that the mass of the atmosphere itself isn't dominating the cluster mass, and it turns out it doesn't. This graph shows the breakdown of the three components: galaxies in yellow, the hot gas in red, and dark matter in grey. The hot gas does weigh more than the galaxies, but the dark matter is 5 times heavier than both these put together. Now, the final method of measuring cluster masses is really quite wonderful. So deep and so extended are the gravitational fields of the rich galaxy clusters that they actually bend passing light rays, and astronomers call this a gravitational lens. Now, in practice, what happens is that the distant background galaxies seen through the cluster appear distorted. Some are even stretched into long, thin arcs. Now, as you might imagine, the degree of distortion reveals the strength of the gravity, and hence the mass of the cluster. The cluster masses measured this way agree perfectly with the other two methods, and they contain much more mass than is just in the galaxies or the atmospheres combined. So I hope by now I've convinced you that dark matter is real and it's a major component in the universe. But apart from keeping astronomers busy, what's it good for? What does it do? The answer is a lot, and without it, we wouldn't exist. As these sequence of images shows, the primary role dark matter plays in cosmology is in transforming a smooth young universe into a lumpy old universe. Stated simply, gravitational clumping requires mass, and the atomic matter alone isn't enough. In fact, in a universe without dark matter, not a single star or galaxy would have yet formed, and probably never would. So dark matter really plays a very important role, and it's something we'll look at in more detail in lectures 17 and 22. Let's consider that third question about dark matter. What exactly is it? What is it made from? Well, the simple answer is we don't know. But that's not quite fair, because we do know a few things about it. For example, we do know it is not any kind of atomic matter like failed dark stars or planets or rocks. We know this because of evidence coming to us from the early universe. In lectures 16 and then 25, I'll show you how the microwave background and the abundance of light elements both tell us that the total atomic content of the universe is just 4%. So the dark matter, which is measured to be 23%, can't be atomic matter in any form. Instead, it's likely to be some kind of relic particle left over from the Big Bang. Now, the fact that these particles are so elusive suggests that they only interact with matter via gravity and the weak force, making them sort of a little bit like heavy versions of neutrinos. Now, actually, we know they're not neutrinos, because neutrinos travel too fast to allow the growth of small-scale clumping. Computer models with this so-called hot dark matter lead to a universe with only huge structures, with few smaller structures like stars and galaxies. Instead, computer models need what is called cold dark matter, with heavier, slow-moving particles that can easily clump up and generate small-scale structure. Now, so far, no known particle fits the description. And in the absence of any further knowledge, astronomers often use a generic term, WIMP, for weakly interacting massive particle. Now, lastly, there are several groups in the US and Japan and Italy and the UK who are trying to detect dark matter particles here on Earth using very sensitive particle detectors shielded deep underground where they're free from other spurious signals. It's a very, very difficult experiment. In total, at any given time, there's only about 1 kilogram of dark matter particles within the Earth's volume. And these particles almost never interact with atoms. But calculations suggest that very occasionally a dark matter particle will smack into an atomic nucleus and knock it backwards. And it's this recoiling nucleus that's ultimately detected. Now, as the years have gone by, the sensitivity of the detectors has gotten better and better, but still, no dark matter particles have yet been found. But if or when they are, it will be one of the most important discoveries of this century. And it'll certainly earn its team the Nobel Prize. I mean, after all, it's not every day that you find the stuff from which most of the universe is made. Now, in the remaining time, I want to talk about the other enigmatic component, dark energy. And to help get started, you need to have some kind of mental image of what it is. So for the moment, just think of it as the energy of space itself. It's not much. It's about a flea jump's worth of energy per football stadium worth of volume. But when you average over the universe, it turns out to be the dominant component, weighing in at 73% of the total. Let's first look at the evidence for dark energy. Like dark matter, dark energy is utterly invisible. But unlike dark matter, it's spread uniformly throughout the universe, so its gravity doesn't affect local motions. It only affects global cosmic expansion. Now, for reasons we'll get to in Lecture 12, the key property of dark energy that makes it so unique is that its gravity causes the universe's expansion to accelerate and speed up. See, ever since Hubble discovered expansion, everyone thought its rate would be slowing down, since the matter within the universe pulls back. So it came as a huge surprise in 1998 when 2 independent teams, led by Saul Perlmutter and Brian Schmidt, found that the universe's expansion was actually speeding up. Now, their method is simple in principle. Here's a standard Hubble diagram, with distance plotted against expansion speed, with the local gradient, slope, giving us the current Hubble constant of 22 kilometers per second per million light years. Now, if you go to greater and greater distances, you're looking back in time. So if the curve gets steeper, we know that the expansion rate was faster in the past. So the universe would therefore be decelerating. But if the curve gets shallower, the expansion rate was slower in the past, and we know the universe would be accelerating. One needs to look very far away to go far enough back in time to see the changing expansion rate. So it's supernovae, like the one shown here, that are used to measure these huge distances. Well, in practice, of course, life is a bit more complicated, and instead people plot not the distance but the brightness of the supernova against their redshift. And they look for deviations from what's expected for a constant expansion rate. Here you can see the data fit the accelerating universe much better than the decelerating universe. So, in the time actually since that discovery of dark energy back in 1998, the supernova data have gotten steadily better, And there are now actually two other independent methods to check for acceleration, and they also give the same positive result. So observationally, at least, it looks as though dark energy is here to stay, and we need to fold it into the cosmological picture. So what exactly is dark energy? Now, the honest answer is, again, we don't know. Actually, the situation is even worse. We really don't know. Now, having said that, there are some ideas. In fact, something resembling dark energy was even introduced by Einstein himself when he added what's called the cosmological constant to his equations of general relativity. His aim was to find a static cosmological solution, a universe which neither expanded nor contracted, because he thought that was how the universe was. Of course, he famously discarded that result as soon as Hubble discovered that the universe was in fact expanding. Now today, cosmologists usually consider three possibilities for the nature of dark energy. The first is a fixed, very slight energy associated with space itself. It's called a vacuum energy. The second is a slightly different kind of vacuum energy, one that varies in time or place, and it goes by a different name, quintessence. And the third involves a genuine modification to the properties of gravity, something beyond Einstein's theory that we don't yet understand. Now, the current favourite amongst cosmologists is the first of these, vacuum energy. So let me look at that for a moment now. Now, I know it seems a bit like an oxymoron that the vacuum, defined to be completely empty space, can actually contain energy, but a modern physics view of the vacuum does actually allow for this. The part of physics that treats the vacuum is called quantum field theory, and it sees all of space as permeated by fields that, in a sense, embody the laws of physics. They also bring the vacuum alive in the sense that within empty space, pairs of particles and antiparticles are constantly forming and dissolving all the time. So with this more active view of the vacuum, I think you can see that perhaps these quantum fields might actually weigh something. They might have some energy associated with them. Now, it would be nice if quantum field theory was able to predict the energy of the vacuum, but it can't quite do that properly. In fact, the best estimate, which is probably oversimplified, gets a value about, wait for it, 10 to the 90 tons per cubic inch. So that's clearly wrong by any standards. So I think at this point the optimistic statement is that finding the nature of dark energy is one of today's greatest challenges in physics. Finally, what role has dark energy played in shaping the universe? Well, so far, not too much. It played almost no role in the early universe, and only recently has begun to gently accelerate cosmic expansion. But its primary influence, so, is going to be on the future, and in two rather distinct ways. The first is that the accelerating expansion shuts down the assembly of structures in the universe. See, ever since the Big Bang, gravity has been bringing things together into clumps on all scales, from stars to galaxies to the web. And as you might imagine, gathering things together in a universe that is expanding is a rather delicate balance. And it turns out that our universe is sufficiently close to that balance that when its expansion changes from decelerating to accelerating, then the clustering stops. So the universe's current web-like pattern won't change anymore. It's now become frozen. But the second effect of dark energy is in some sense more dramatic. It drives an exponential expansion that doubles the separation of galaxies roughly every 10 billion years. So as the trillions of years pass by, all parts of the universe get further and further from each other, moving faster and faster. So the universe becomes more and more empty. But it's worse than that. Not only are things far away, the space they're in is moving faster and faster. And in time, every galaxy passes light speed, at which point we say it crosses an event horizon and becomes forever invisible. Ultimately, the only things visible to us will be the stars and galaxies that are in our immediate vicinity, their mutual gravity winning out over cosmic expansion. Who would have thought that such an apparently innocuous vacuum energy, a mere 6 milligrams per Earth volume, could so utterly affect the future of the universe? Let's end this lecture and this first overview theme of 9 lectures by returning to that remarkable and sobering truth that 96% of the universe's contents are not only beyond our senses, but also beyond our current understanding. This is, however, a wonderful situation. We know there is more to the universe than meets the eye, literally, and there are great discoveries still to be made.